Okay. Hi, everybody. I'm Benzi from SCALEMP. And what we'll be talking about now and showing a demo of is using large memory on public and private clouds. So I apologize in advance. My demo is going to be short because it's very, very simple. I'm showing you a couple of slides just to explain what you're about to see. And then we'll go into the terminal and see it in action. So why do you want to use large memory at all? What's important? Well, there are three types of workloads that are very common on clouds, and they either benefit or require large memory. The first is if you're running many VMs, many containers, typically you're running out of memory. So if you want to put more on a platform, you would typically need more memory. So that's easy. That's number one. Allows you to have more density on your workloads. The second one is if your workload itself uses a lot of memory. For example, if you have an in-memory database like SAP HANA, or if you have an in-memory cache like Redis and so on, those workloads require to have more memory. Okay? So again, more memory is essential to them. And the last one is where you want to do in-memory computing, AI, Apache Spark, these type of workloads, genomic workloads. Those workloads are workloads that eventually require more memory. And if you don't have more memory, you can't run the workloads that you want to run. So these are the workloads we're targeting here. And so what's the problem with that? Why is having this need for more memory a problem? Well, DRAM, which is memory, has two main issues. A, it's expensive. It's way more expensive than any other media. Okay, and we're talking about $7 or so for the run-of-the-mill memory, and then as you grow, if you're looking at higher density modules, you're looking at much higher cost. So that's one end of that problem, and the other problem is that DRAM doesn't scale. Okay, so what I'm going to show you today in the demo is essentially a way to solve this, a way to have more memory without needing to pay as much as DRAM costs and without being limited at the scale. And with that, I'll just move to my first demo. So I am connected to a system. Let's do this. Connected to a system. The system runs. So this is an in-house, on-premise type system. It's in New Jersey. It's hosted in New Jersey. And if I look at the CPU that it's running, you can see that it's running Intel Skylake dual socket gold environment. And these systems, these CPUs, they cannot take more than 1.5 terabytes of memory on two sockets. So 768 gigabytes per physical CPU. That's limiting, as I said before. That allows you to not maybe use all the VMs I want to use or containers on a node and so on. This machine actually, running the SCALEMP technology, has 4.2 terabytes of memory. Right? So how does that happen? How do I have so much memory? You can't even plug enough DRAM into the system to get to such high memory. Well, the way we do this is we use non-volatile media and transform it using software, advanced software, into memory, byte addressable, high performing, just like you installed more DRAM. Okay? So what we're showing here is a completely transparent, nothing special, regular Linux environment. Haven't done anything to it. Your applications don't need any recoding. Your operating system is the one of your choice. You want to use Ubuntu, use Ubuntu. You want to use Debian, CentOS, Red Hat, whatever, SUSE. All of them work. And there's really no way for the application to know anything about that expansion. It's completely transparent. If I do NumaCTL-H to show me what the memory architecture looks like, I just see two NUMA nodes with CPUs and a lot of memory on them. That's it. There's nothing special in that machine that makes me need to redo my code, do anything different than I have done before. If I want to see really what's underneath, there's a special interface we provide to our software. Our software loads first before the operating system. And there's a special way to talk to it. If I use that, then I will see exactly what's installed in that system. And we can see that I have a system motherboard that has processors and I/O and memory on it. And then I have here 6 devices from Intel. Those are NVMe devices. And these devices here, 5 of this type and 1 of this type, provide the additional memory to my system. So these are actually NVMe devices, PCIe. You buy them from Intel, you plug them into your systems. That's for on-premise. We have the same solution from companies like Western Digital. And that gives you the added memory. And you can see here, I have 300 and something gigabytes of DRAM installed into the system, and then additional several units that provide 650 gigabytes each to have a total of 4-point-something terabytes. Right? So we have leveraged non-volatile media, in this case, the Intel Optane. So you buy this solution for your in-house deployments, for your private cloud. You buy that from Intel, or you buy the competing product from Western Digital, and you plug it into the system, tell the system to boot from it, and you're done. You have more memory. It's that simple. Now, all the rest of the devices on the system are the same. You've got nothing else that's special. So, except for those PCI devices not showing up because they're used as memory, all the other ones, the SATA controllers, network controllers, everything is there. Your system is just as it was as before. What I want to show you also is a similar thing running on a public cloud. So I'll move to this machine here. This is an instance on the AWS Cloud in this case. Okay, we have multiple clouds already running this. It's available on AWS. It's on the marketplace for AWS. It's called Memory One. You could get this in beta now on the Oracle Cloud. Talk to us if you want to do HPC, bare metal. Oracle Cloud is great for that. We have this in small niche cloud players like packet networks, where you can have a system with more memory that way at a very low cost. And what I'm showing here is an AWS instance, an EC2 instance. And again, let's look at which CPUs this instance has. And so this is an EC2 instance that has, let me make a bigger font here. CPU instance that has these previous generation CPUs, codename Broadwell from Intel. And again, if you know this platform, you know that you cannot put more than 1.5 terabytes on this platform. Just impossible. Actually, it has less on the Amazon cloud. It has about half a terabyte. But this specific instance type, certainly, even if Amazon wanted to, they cannot plug more than 1.5 terabytes of memory into it. So again, if we look at the amount of memory I'm seeing on this Amazon instance is 4 terabytes. So it's 4 terabytes of memory running on an Amazon instance that has barely a half a terabyte of memory. If you look up how much it costs to lease a 4 terabyte instance from Amazon, it will be close to 30 terabytes close to $30 per hour. So we're talking about having something that costs $30 per hour, roughly, at less than $10 an hour, because this instance is way cheaper. But you still get the memory that you need. So I want to show you what it looks like, again, with that same command that we used before. So as you can see here, I have the Amazon devices, those NVMe devices that come on this Amazon instance. It's one motherboard that has the processors and I/O and so on, and then 6 of these NVM devices, 6 of these Amazon NVM devices. In this case, you see that half a terabyte comes from the actual DRAM, and then all these other devices each contribute roughly 600 gigabytes. We're over-provisioning them. You see the devices themselves have about 1.8 terabytes total of storage capacity. We're not using all of that. We're using only a third of it. That delivers more performance. So in NAND NVMe devices, if you over-provision, you get a lot more performance, and we take advantage of that. So again, this instance gives you 4 terabytes on a public cloud without needing to do anything special. You just run the Memory One, SCALEMP Memory One AMI, and then you load your own AMI, your own operating system and environment that you choose. And it comes up, you have 4 terabytes that you can use. You save more than half the cost, right? From $30 roughly to less than 10. And you're getting the performance that is just like DRAM for your in-memory applications, near DRAM performance at much lower cost. And you could actually expand more. So it depends on the instance of your choice, which instance you chose, how much memory it has, how many NVMe are on it, that you can choose to expand. Let me just quickly show you if I do this. So you will see that we still have 2 NVMe's here available for any I/O work that I want to do. 2 block devices that I can still use. If you look up this instance on Amazon, you would see that it has 8 NVMe devices. So I took 6 away, made them memory, and then the other 2 are still available. If I wanted a different balance, if I wanted to just take 4 of the devices to make the memory and 4 of them to use for storage, fine. It's all up to you. You do exactly what you need. You pay exactly for what you take, just the cloud way. Right? So we have this ability to now expand memory way beyond system limits, way beyond cloud limits, wherever you're using your systems in-house or on a public cloud, you could actually set them to be much larger memory. Going back to what we talked about before, that allows you to then be more cost effective and efficient when you put more VMs or more containers on a node, or when you have a smaller Redis or Apache Spark cluster, because you have more memory per node, you need less nodes to host your data, or to run larger and larger HPC models, simulations, and so on, AI, use more data for that and still get the data results really fast because you're running everything in memory. So that's that. From a block diagram, what does this look like? I just want to quickly show you what it means when you move from a DRAM separate from storage into something that's hybrid. So on the left, we have the system. You got your compute, you got your memory, and you got your storage devices. On the right side, as you can see, between the operating system and the hardware runs a thin layer of software-defined memory, basically taking part of that high-end storage, turning it into part of your memory. So now it's one memory pool out of your DRAM and your high-memory storage devices, non-volatile media, which is, of course, much lower cost, much larger in size. So you can get much lower cost overall memory per gigabyte and much larger than you would otherwise be able to get. And the OS running on top of this knows nothing. To it, it's just a big machine. You just bought more DRAM and plugged it in. It doesn't know that some of it is NVM. So it's completely abstracted and virtualized so that the OS and hypervisor and whatever else you run up there for applications don't know and don't need to know about it. They just get the service that they need. And with that, I'm done, and I'm happy to take any questions or talk more about the Amazon instances or the upcoming other cloud vendors that we're going to support. Okay, if no questions, I'd like to say 2 more things. Our booth is over there. I'm happy to talk to you. Just stop by. I'm going to be here till the end of the day. So we're at the booth, and please come talk to us. We can help you. And if you're not sure if your workloads can benefit from the large memory, we're happy to tell you about other customers. This thing is already in production for 2 years with major cloud service providers and hyperscalers. So that's one thing I wanted to say about it. Our booth is there. And the second thing is, if you have any other need, like you want to use a different cloud provider, you have a cloud provider in China that you want us to support, send us an email to memory1@scalemp.com. Let us know which cloud provider you want to use, and we'll onboard that one as well. Thank you.